Hello, I am Neeraj. Today I will try to discuss about saddle points. Actually, saddle points and local minima are among key important challenges that all deep learning and neural network based architectures generally face. So, in this tutorial, I will try to consider three important things. First, what is saddle point, how it affects the learning process. Second, how we can identify the saddle points, and third is how we can escape from the saddle point situation. So, in the traditional deep learning based architecture, where we use the gradient descent based methods, so learning happens, we learn the new value of any neuron by using old value of that neuron minus learning rate into del f with respect to del x. And suppose we have another variables, then we learn its weight equal to y old minus learning rate into del f with respect to del y. So this is the process to learn. So here you can assume in this scenario also we have a simple neural network architecture with input I1, I2 and all the connected neurons. Here you can see that assigned some initial random weight x1, x2, y1, y2, x1 dash, y1 dash like that, and then it generates the output. So when we apply the gradient descent based methods, so these neuron weights get updated through this process. But what happens due in the general case? In general case, what happens when we reach the global minima? The value of del fx, del f, and then del x becomes 0, and then del f means partial derivative with respect to y becomes 0. This happens in the global minima. So this is the ideal case of learning. But in the case of saddle points, we will get some points where instead of reaching at global minima, we get the partial derivative equal to 0. So those points will be equal to saddle points. So now the scenario is how the saddle points affects the learning. So here the scenario is we are not at global minima, but we have partial derivatives equal to 0. This means learning stop, means no learning. No learning means no weight updation. So this is the way saddle points affects the learning. Now let us go through some simple examples. Like we have functions fx is equal to x3. All those figures and equations are actually taken from research papers and external sources. In the description box, I have properly given all the resource related references. So it is given that at x is equal to 0, this shows as saddle point scenarios, means x is equal to 0 is a saddle point for these equations. So we can understand this when we take the derivative of fx with respect to x, then it becomes 3x square, and when we evaluate with respect to 0, then it gives x equal to 0. So partial derivatives at x is equal to 0 will be equal to 0, means at x is equal to 0 the system will not learn. So this is the saddle point for these scenarios. Now we can try to check with other case, like we have a hyperbolic paraboloid. So here you can see that this is hyperbolic paraboloid, and it is given that at x is equal to 0 and y is equal to 0, this again shows, means x is equal to 0 and y is equal to 0 is a saddle point for this system, means a plane which passes through tangent, means a tangent plane which passes through x is equal to 0 and y is equal to 0 actually shows saddle point property. So we can check it. So when we take the partial derivative of fxy with respect to x, we will get like 2x, and when we take the partial derivative of xy with respect to y, we will get minus 2y. When we evaluate this with respect to 0 0, then for this also we will get 0, and for this we will also get 0, means when we take the 0, then this will indicate that x is equal to 0 and y equal to 0. So this means at x is equal to 0 and y is equal to 0, the derivative of this hyperbolic paraboloid will be equal to 0. And at this point where this derivation is 0, and the tangent plane which passes through x is equal to 0 and y is equal to 0 will contain some saddle points, and the system which are using such kind of scenarios will not learn at x is equal to 0 and y is equal to 0 kind of scenarios. So in this case what will happen, let us try to assume that some x-axis and y-axis is there. Then for some axis you can see that this point is a little minima kind of thing. This is a minima, local minima, and for some other point, if you see from this angle, then you will find that it is coming under some maxima point, local maxima point. Means if you take it against x axis, then this is our local maxima, this is local minima. So if we closely observe this scenario, we will find that we got three properties. First, partial derivatives at a given point xy equal to 0 0, or some other points for some other equations is equal to 0. Second is, at the same point you will find local maxima also, and at the same point local, through some different angle, local minima will pass. So these are some scenarios, properties, and how it affects the learning process. So these are the things that we covered till now. So now let us try to understand how we can identify the existence of saddle point in a higher order variable systems. So for this we generally use the second order partial derivative test, and for the second order partial derivative test we generally use the Hessian matrix, which is a square matrix which contains the second order derivatives, all second order derivatives of a given function f. So in the current scenarios we are just taking the hyperbolic paraboloid functions. So in that case, if we have just two variables x and y, so in this case our Hessian matrix will be given by f x x f x y, f y x, and f y y. Actually, f x x is equal to second order partial derivative with respect to x. So in this case, if we take fxy is equal to x square minus y square, so our fxx will be equal to del. So first order partial derivatives when we take with respect to x, then definitely this will be a constant part, so we will take this derivation only, so it will be 2x. Again when we take the derivations, the output will be 2. Similarly, f y equal to so when we take our fxy, so it will be like I'm taking with a little so it will be when we take this part will be constant, this will be taken against this first derivatives with inside the bracket, so it will be delta with respect to delta y minus 2y, and final outcome will be minus 2. Similarly, we can take the fxy, so it will be defined like delta x with respect to y, and when we take the computation for this part, it will be so when you take the first partial derivative of this function with respect to y, so only this portion will be considered, so it will be minus 2y, but here we are taking the derivation with respect to x, so it will be considered as a constant, so derivation will be equal to 0. The same thing will happen here also when we take the derivation with respect to y. Here we took the derivation with respect to this term only, we neglected this because we are taking derivation with respect to x. So again we are taking the partial derivation with respect to y for x, so it will be treated as a constant, so the derivation will be equal to 0. So for this function, the derivation will be equal to 2, 0, 0 and minus 2. Here you can see the values like that. Now the next step is to compute the determinant of the Hessian matrix. So the determinant of this two order Hessian matrix will be equal to just fxx into fyy minus fyxy into fyx. So this is the computation scheme. Now we are assuming that we have some critical points. xy equal to 0 0, where our first order derivation x xy will equal to first order derivation fxy equal to 0. So at this critical point, we assume that in the computation of Hessian matrix determinant, we have fxy equal to fyx. So we will improve our equation for this critical point like fyy minus fxy square. Now this is the very important equation which derives the characteristics of local minima or maxima, because Hessian matrix we generally use for that purpose only here, and to identify the saddle existence of saddle point. So if this is negative, if f(x)s is negative, then it will result in a negative concavity for x-axis. If it is positive, then it will show positive concavity with respect to x-axis. Similarly, if yy is negative, then it will show the negative concavity with respect to y-axis, and if it is positive, then it will show positive concavity with respect to y-axis. So in that case, so if determinant is greater than 0, then there will be two conditions. First is if fxx is greater than 0, then there will be local minima at our critical point xy, and if fxx is less than 0, then there will be a local maxima at our critical point. Now the second option is, if our determinant value is 0, then there will be a saddle point at our critical point xy, which we took 0 0. But third condition will be, if d equal to 0, then it is undecided kind of situation. It will contains local minima, local maxima, or saddle point. So anything is possible. Now the value of this determinant or these scenarios will depend upon these three things: fxx, fyy, and fxy value. So here you can consider that if it is negative, and if it is also negative, then value will be something positive, and if it is some value e, then the chances of getting determinant greater than 0 or determinant less than 0 or equal to 0 depends upon this value that is coming from here. But if here something positive and if something here negative, so in that case, whatever the value will be here, the entire determinant will be less than 0, because this multiplication will be something negative. And same thing will happen if fxx is negative, and if it is the positive thing, then whatever the value here, the determinant will be negative. So same thing. So this means some positive and negative concavity is just x and y axis, some positive concavity or negative concavity is actually the creating the issues. For example, here when we had created the broken the graph in x and y directions, we find that at some point it creates positive concavity, at some points it creates negative concavity. So this means in this scenario and in this scenario we will have something contradiction kind of things, such kind of contradiction. So such points we mentioned that at first order derivations at that critical point will be 0, and we will have some contradictions. At the same point we will have local minimum from one side and local maximum from other side. So such kind of derivations we can get here with the help of our Hessian matrix. But this case is little confusing. So, and to get the information at higher level, we use some concept of eigenvalue. So in this case, we just calculate the eigenvalue for a given critical point. So suppose in case 1, at a given critical point A, our eigenvalue are of same sign or positive, means all eigenvalues are positive. Then there will be a local minima at A. And similarly case 2, for a given critical point A, all eigenvalues are negative. So in that case what will happen? A local maxima, just opposite, at A. And similarly in case 3, if at A, critical point A, eigenvalues are opposite sign, then there will be a saddle point at A. So in this case, surprisingly, in this case, if you try to get the eigenvalues, you will get one eigenvalues as +2 and one eigenvalue as a -2 for this Hessian matrix. So definitely this means there will be a saddle point, and we have identified the critical point as 0, 0. So at this point we will have saddle point. The next part is how we can escape from the scenarios of saddle points. So to jump out and to reach to the global minima, we generally apply multiple different ways. So first way is just like try with some condition to check the existence of saddle point. If yes, chances of saddle points are there, then make a little change in your learning process. So in this case, weight updation process will be little different. Minus learning rate into plus some little constant value. Else that constant value will be greater than 0, something greater than 0. Here it is a learning rate. Otherwise, you can continue with your old system, like as it is we are using. Means there is a no constant weight here. This is not here. In the other case, second is, it is already proved that momentum based method for gradient descendant descent actually helps in coming out from the saddle point scenarios. So for momentum based method, I have already prepared one video that you can watch. I have given the link in the description box. Now there is a third scenario also. So third scenario is to add the second order Taylor series. To use the second order Taylor series, but the problem is the computation in the when we calculate the gradient, we generally face a lot of overloads of computations. So in that case, computation of a second order Taylor series is not very useful technique, and that's why it is not used in several places to escape from the saddle point scenarios. Actually, it solves the scenarios or situations of the saddle point system, but generally we use these two cases to handle the cases of the saddle points. That's why I am not covering the second order Taylor series. But if you are interested, then I have given the link of the paper which describes the second order Taylor series to escape from the saddle point in the description box. So thanks for watching. I hope that you have enjoyed this very simple and easy tutorial.